first speaker this afternoon is Rob Spekkens from our nearby neighbor institute, the Perimeter Institute. And he's talking about the invasion of physics by information theory.
Thanks, Wayne, for inviting me. So this talk is going to serve as a bit of an introduction to the notion of resource theory, so hopefully it'll be useful for some of the speakers that are coming later in the conference. But the overall thesis is going to be something about the importance of information theory in physics. And so I'm going to start by telling you what I think the role of information theory is in physics. And to do that, I want to contrast two kinds of revolutions in physics. So the first kind is sort of the standard one, where some theory gets supplanted by a new theory that makes different empirical predictions and then is tested experimentally and vindicated, and the old theory is rejected. But the other kind of revolution is one that happens, more gradually. So the first type of revolution, typically you sort of can pinpoint exactly when it happened. The second type happens more gradually, and I would characterize it as a change in perspective on existing physical theories without overthrowing them. So I think nice historical examples, we'll see what happens. So the use of action principles, least action principles, symmetry principles, thermodynamic principles. If I take the first example, so the work of Lagrange and Hamilton in the 18th and 19th centuries didn't overthrow Newtonian mechanics. It did change significantly our perspective on Newtonian mechanics. It vastly expanded the scope of areas in which we could apply those notions. But it didn't overthrow it. It did, however, pave the way for the revolutions that did overthrow Newtonian mechanics. So the quantum revolution, for example, built heavily on the use of least action principles and thermodynamic principles, or the invention of quantum electrodynamics, for example, which appealed to symmetry principles and also in the work of De Broglie, least action principles. So that's the kind of role I see for information theory, that we can reconceptualize existing physical theories from the framework of information theory and get a new perspective on them, perhaps generalize them, solve some new problems, and hopefully this paves the way for what's to come. And it may, in fact, be critical for figuring out the next theory. Okay, so there's lots of things you could say about how information theory is changing how we think about problems in physics. But this talk is going to be specifically about how it's doing that in the context of resource theories. So I'm going to start out by talking a little bit about what resource theories are, and I'm going to be summarizing what's in this paper, which is a particular approach to understanding sort of abstractly what a resource theory is, independently of which concrete example you have in mind. The first thing I want to say is just how does the resource theory approach sort of get characterized philosophically? I would say you can distinguish two kinds of approaches to physics, which I think have historical precedence. There's the dynamicist approach, where you imagine that the job of a physicist is to describe the natural dynamical behavior of a system without reference to agents or their purposes or anything like that. So sort of the God's eye perspective on what's happening in the universe. Whereas the pragmatist approach is about characterizing the in-principle possibilities of what agents may be able to control or what they may be able to know about physical systems. And I think this is a perfectly fine way to do physics, because it's not about characterizing, what I can do with this particular gizmo that I have today, and in 10 years they're going to be able to do something different. It's not parochial in that sense. It's what do the laws of physics impose for any agent in the universe in terms of what they can know and what they can control. So it's just as much about what the fundamental laws are. It's just a question about what the fundamental laws imply about what agents can achieve and do in the universe. So it's that particular angle on the laws, trying to understand them from that perspective. So resource theories take that pragmatist approach. Okay, well, let me start by just giving you a few examples. We're going to go into much more detail later. But I would say in the quantum information foundations community, the first good example of a resource theory was entanglement theory. So the idea was in the early days, people didn't think of entanglement as a resource, but in the 90s, suddenly people realized that if you have entanglement, you can do something interesting with it. And it was also realized that if you have two parties, Alice and Bob, and they only have a classical channel between them, but locally they can do quantum operations. Things can be quantum coherent locally. It was realized that if you have that, then they can't generate entanglement. But if somebody gives them some entanglement, they can use local operations and classical communications to manipulate it and do interesting things. And in particular, they can lift that restriction of having only a classical channel using the teleportation protocol. They can simulate one use of a quantum channel if you give them 2 qubits that are entangled. So in that sense, this entanglement is a resource. It gets used up. It allows you to lift the restriction. So thereafter, people started thinking about entanglement as a resource and questions about, what kinds of conversions can you make among entangled states. And that pattern has now been repeated many times for different kinds of properties of quantum states, different kinds of phenomena. So I'm going to be talking about these 2 resource theories. So the resource theory of asymmetry. So there, what's free, the analog of local operations, classical communication, are operations that are symmetric. So for example, it might be rotational symmetry. So imagine you can only do things that are rotationally symmetric. Under that restriction, if somebody gives you a state that breaks rotational symmetry, that's a resource. You can now do new things with it. You could use it, for example, to rotate another system, which would be a rotationally non-invariant operation. And similarly, athermality theory is a resource theory where what's free are thermal operations, and I'll define what those are later. But essentially, there are sort of things in thermal equilibrium, and then the resource becomes any deviation from thermal equilibrium. And the question becomes, how can you convert between resources corresponding to different ways of being non-equilibrium? So that's sort of the pattern, and there's a long list of resource theories you could be interested in. And what I want to tell you now is just a little bit about the abstract structure, something that you can awake to conceive of all these particular concrete examples. So you start with what I'll call a process theory, and the idea is it's just you have some systems that maybe have different types, which I'll just label A, B, C. So in the context of this talk, we might be talking about a spin-a-half system or a spin-1 system, have different representations of the rotation group, or maybe a system with one type of Hamiltonian or another type of Hamiltonian. So there's a distinction among types of systems. And then you have a whole bunch of processes you might implement. So F, for example, could be a process from A to B, and so on. You can have processes on pairs of systems. You have processes that go from the trivial system, nothing, to some non-trivial system. We usually call those states. And you can combine these things now in parallel or in sequence, as long as the types match. So that defines a process theory. So quantum mechanics, for example, is a process theory where I have quantum states and quantum operations, which I can combine together. And now what you do is you identify a subset of those, which I'll call the subtheory of free processes. So you stipulate that some subset of these guys are free, so you're not going to account for their cost at all. But you still require, for example, that I can compose them in sequence and in parallel, and anything I get from a starting set is also considered free. So if it can be built out of free stuff, it's free. And that means that if I choose this set poorly, it might turn out to be trivial, right? So if I choose too many things and I close under all possible combinations, maybe I get everything. And then I say, oh, I haven't actually stipulated a proper subtheory at all. I've just sort of said everything's free. So to have something interesting, you need to find a set of things that you can allow to be free, which doesn't give you everything in your theory. That's where the structure comes from. Okay, that's when you have an interesting resource theory. So a resource theory in this language is a partitioned process theory. It specifies some enveloping theory and some part of that theory constituting free stuff. And the way we formalize this in the paper I mentioned is using category theory, and then the free stuff is a subcategory. And let me just mention that we were talking about this over lunch, that you can, for a given category, there's only so many strict subcategories of that thing. It's a well-defined mathematical question. Just like if I give you a group and I say, what are all the strict subgroups? You can go and work that out. It might be an infinite number, but there's some classification. Well, it's the same thing here. If I give you a process theory and say, what are all the strict subcategories of it? That's a well-defined mathematical problem. There's no arbitrariness. There's just a fixed number of subcategories. And for every one of the category-subcategory pair, I get a possible resource theory. So there's something very non-arbitrary about these resource theories. They're sort of, they're there in the mathematics, right? So there's only so many non-trivial resource theories I can express in quantum theory. Okay, so the main question that people ask in resource theories is about conversions of resources. So if I consider a pair of states, for example, R and S, I want to know, can I get from R to S by free processes, things that I've allowed for free? So in this case, I need a process that goes from type A to type B. So if there exists a free process that'll do it, then I say, yes, R goes over to S. But I can ask the same question of processes, for example. So if this is an A to B process, I want to know whether it goes to C to D. Well, there's some other processes which will change the types in such a way that I can take something of this type to something of that type. And if I can find some free stuff that allows me to do it, then yes, F goes to G. And for any arbitrarily complicated process you have in mind, I can ask about whether I can do a conversion. I can ask about conversions between transformations and states, or states and transformations. All that stuff is allowed. So ultimately what you get is, for all the different processes in your theory, you get a big partial order, which tells you something about where you can go into the free operations, right? So an arrow in the partial order means I can get from here to here using that free set of processes. And in general, it's not a total order. It's really a partial order. So here's a little fragment of a partial order where R2 and R3 are not ordered relative to one another. So here, R1 can be converted by free operations to R2, and similarly here, but I can't go either way between R2 and R3. And that's kind of critical. That's going to end up being a really important thing, that typically resource theories involve partial orders. And so one of the consequences is that when you try to measure how much of a resource you have, typically you're going to need more than one measure. So what do I mean by that? First of all, how do we define a measure of a resource? Well, here's the idea. A function m, which is just from your set of resources to the reals, is going to be said to be a measure of the resource if whenever you can convert R1 to R2 by these free processes, then the measure is larger on R1 than it is on R2, or not less than it is on R2. And so that just means that a measure of a resource should be something that is not increasing under this free processing. Right? The free processing cannot increase the measure of the resource. That's the intuitive notion. So in other words, this measure has to respect the partial order. If R1 is above R2 in the order, then the measure has to be higher on R1 than it is on R2, or not higher on R2 than it is on R1. So in particular, if we look at that little partial order I showed you, there could be one measure which carves it up this way, right? So for every one of these different regions, it assigns a different value. The highest value goes for R1, then R2, R3, R4, R5, which gets the smallest value. But I can also carve it up this way. This would also be a valid measure because R2 and R3 are not ordered, so I can make the value of the measure higher on R3 than it is on R2 if I like. That's also satisfying this constraint. And now the point is that any given measure always induces a total order on the states, and so it doesn't capture the partial order. If I just tell you the value of an individual measure, you can't figure out where you are in the partial order based on that value alone. Or you can't know what the partial order is based only on the value of one measure. Typically, you need multiple measures. So in this example, I would need to know the values of M1 and M2 to learn that R2 and R3 are not convertible one to the other. And I could deduce the partial order from knowledge of this pair of measures. So the bottom line is if your partial order of resources is not a total order, then there's no one measure to rule them all. There's no, we have to find the right way to quantify this resource. That's just the wrong way of thinking. I call it the total order fallacy. And I think physicists fall prey to this all the time. I've got this new measure of a thing. It's the right one. It's the best one. It's got all these nice properties. No, the deep thing is what's the partial order of resources under conversion, and typically there's no single measure that captures it. You need a set of measures. So the only interesting question for measures would be, what is a complete set of measures? One that totally characterizes the partial order of resources. Okay, so that's it for the general stuff on resource theories. I'm going to have a very short section on a resource theory of information. I'm not going to say a lot about it, but it's going to inform what comes later. So what do I mean by information here? I'm going to be talking about quantum information. I'm going to be talking in particular about quantum encodings of classical data. So this arises a lot in quantum information theory. So the resource of interest here is just some set of quantum states labeled by some classical variable. So this is how quantum information theorists encode information. You know, in a classical world, you could say, well, for every value of this message, for every possible message I want to send, I might use like a distribution over the physical states in my channel. Here, it's a quantum state for every message I want to send. And so, you know, the recipient's task might be to distinguish these different quantum states to try to learn what the classical message was. The free operations are just any processing on the system that represents that data. So I can do the most general kind of processing in quantum theory is a completely positive trace-preserving map. So I can apply any map I like to that system. And that's free. What I can't do for free is just get a new encoding of X. You know, so if we're imagining a communication context, Alice has this classical message X. She encodes it in a quantum system, sends it to Bob. Now Bob can do anything he wants with that system, but he doesn't get more copies of X, right? That's in Alice's lab. This quantum system is the only sample he has of X. So he can process it as much as he likes. And now the question becomes, how do I compare different encodings of X? So, you know, here's a set of states rho X, here's a set of states sigma X. To say that this one is a better encoding than this one is to say that there exists some processing I could do to this one that would give me this encoding. So for example, if Bob takes this encoding and adds some noise to it and gets this encoding, then I say, well, I can convert this encoding to this encoding. I can do data processing to get from here to here. And so they're ordered. Whereas if I had a different set of sigma x's such that there's no map that would take me from the rho axis to the sigma x, then I can't achieve that conversion. So relative to that, you know, we get a partial order of these sets of states and how well they can encode classical information. And as I said, you know, the really interesting question is, can we characterize that whole partial order? Can we find a finite set of conditions on any pair of these sets such that I can decide whether I can, you know, one allows me to convert to the other or vice versa, or maybe they're not ordered at all? Generally that's hard, and in the quantum case we don't know what that full set of conditions are, so this is an open problem. We have some special cases where we know the answer, but we don't actually have a solution to this in quantum information theory. But we have some other tools which can be very useful. In particular, we have measures of the resource. So we have measures of information. So let me just adapt the definition I had earlier. So I'll call these functions I now for information. So function I from states, or I should say sets of states, from sets of states to the reals, is a measure of information if whenever I can convert this set of states to this one, the measure of information on the target is not greater than the measure of information on the source. So the definition is just that a measure of information is something that is not increasing under data processing. So that's intuitive, right? By processing the thing, like maybe adding noise, I'm not going to increase the amount of information I, Bob, have about Alice's classical message. At best, I'm just going to turn it into a new form. At worst, I'm going to degrade it. I'm going to have less information about what Alice sent me. So that's just what I said, and classically, this is an extremely intuitive principle, right? Classically, if I encode a bit, say 0 or 1, by sampling from, say, the red distribution if it's 0, sampling from the green distribution if it's 1, and then sending you, whatever value I happen to sample. So this is like the system I'm sending you in its different physical states. I send you the physical system after having sampled it. You can process that system. But there's some fundamental ambiguity as to whether it was 0 or 1. You have a probability of guessing correctly. And no amount of processing of the system you got is going to improve your probability of guessing 0 and 1. The distinguishability of these two distributions is the best you can do. Any processing will just make it worse. And the same thing is true quantum mechanically. If I encode 0 and 1 into non-orthogonal states on the Bloch sphere, for example, processing them might make them even less orthogonal, but it's not going to make them more orthogonal. And so any measure of information should respect that fact. It should be non-increasing under data processing. So people sometimes talk about certain measures of information, and they refer to the data processing inequality. But to my mind, it's not as if proving monotonicity is sort of an interesting thing to do for a measure of information. It's rather that it's the definition of a measure of information. You know, monotonicity under data processing is the key to being a measure of information. Anything that doesn't satisfy it just shouldn't be considered a measure of information at all. Okay, so if you look in the quantum information literature, you'll see lots of examples of measures of information. Here's just a sampler for you. This is called the Halevo quantity. So it's for any distribution P, I can sum up these states with that distribution, calculate the entropy, subtract off the weighted sum of the entropies. That gives me a notion of how much information is in that particular encoding, this set of states. If I have just a pair of states, so I'm just sending a single bit of information, the trace distance between those states is a measure of information. You can prove that. And then there's more exotic ones that involve things like the relative Renyi entropy of order S, and it looks like this. And there's a long, long list of them. There's many things you can prove satisfy this definition of being a measure of information. And as I said, no one of them is really the best, because I, in fact, need a whole bunch of them to figure out what the partial order is. They're all useful in certain contexts. And I'm going to come back to these a little bit later. Okay, so that's all I want to tell you about information theory. And now in the rest of the talk, I'm going to say what its applications are in resource theories that have more to do with physics, that you might think a priori have nothing to do with information. So the first example is going to be the resource theory of asymmetry, by which I mean symmetry breaking. Okay, so the principle that really motivates this theory is Curie's principle, which states that any asymmetry that you find in a physical effect must be found in its causes. Curie used this in the context of crystallography. Now, most physicists I know have never heard of Curie's principle. Philosophers are better in that respect. I find philosophers have heard of it. But every physicist has already internalized this principle because if you do a degree in physics, then you quickly learn that if you've solved a problem and you find that your solution breaks some symmetry, and then you go and you look at the statement of the problem, you look at the initial conditions, they didn't break the symmetry, you look at the dynamics, it didn't break the symmetry, then you conclude you've made a mistake. That if your solution breaks the symmetry, then there has to be some explanation for it in the statement of the problem. So this is an intuitive principle that physicists use all the time. And I would say another principle which is equally well motivated would be a quantitative version of Curie's principle, which is just that if you can measure asymmetry, then the measure of asymmetry in some physical effect cannot be greater than the measure of asymmetry in its cause. So you can think of the resource theory of asymmetry as essentially trying to formalize this notion, this quantitative version of Curie's principle. So let's do it. The first thing we need to define a resource theory is just to define the free operations. So in this case, they're symmetric operations. So here we're working within quantum theory, the theory of quantum processes. And I'm going to describe the theory to you in a generic way, where the symmetry could be anything. So there's going to be some group G. To make it concrete, imagine, for example, it's rotations. That's a good example. But in addition to specifying the group, I have to specify a unitary representation of that group. So that's just specifying something about how any given system transforms, for instance, under rotation. So if it's a spin-a-half system, it has one particular representation of SO3, the group of rotations. If it's a spin-1 system, it has a different representation. So you need to specify that as well. And then, relative to that, you can define a symmetric operation to be any completely positive trace-preserving map that just commutes with the action of the group. So if I take any state and I apply the group action and then I apply my map, it's the same thing as applying the map and then the group action. A cartoon makes that a little bit easier. So it's covariance under this action of the group for all elements of the group. That's the definition of symmetry. Here's an example. So if you take a spin-a-half system whose state space is the Bloch sphere, and you imagine depolarizing it, right? So just reduce the Bloch sphere, change its radius, reduce it. So if you imagine doing that and then rotating, or first rotating and then depolarizing, you get the same thing. So that means that this depolarizing operation is a rotationally symmetric operation, as the picture suggests. So these are the kinds of things we have in mind. We want to imagine that you're restricted to just those operations that have this symmetry property. Now here's something that'll be useful, is that every one of those operations can be realized in a very particular way. This is called a dilation. So it's for any operation you give me that has that symmetry property, I can realize it by coupling the system to some ancilla system that's been prepared in a symmetric state now. So the definition of a symmetric state is one that if I apply any element to the group, it doesn't change. I couple it to a symmetric state by some unitary that satisfies the symmetry. So that means it commutes with the action of this group. And then I trace over some ancilla system. Every symmetric operation can be realized in that way. So for example, that depolarizing operation I mentioned, if I have my spin and I bring it up to a bath of unpolarized spins so that they're starting out in a symmetric state, and I use a Heisenberg interaction, which is a particular kind of rotationally symmetric interaction, I can actually realize that depolarizing map that I described. Okay, good. So now let's ask the main question of any resource theory, which is, what can we say about state conversions? You know, when can I take some state rho that breaks the symmetry to some other state sigma that breaks the symmetry using only symmetric operations? So I'm really asking whether there exists some map which has the symmetry property such that when I acted on rho, I get sigma. And ideally, I'd really like some finite set of conditions on rho and sigma such that I can just answer this for any pair you give me. And so what we're looking for are constraints on state transitions that arise from symmetric dynamics. And when you phrase the question that way, it should sound kind of familiar, because it's usually how we think about Noether's theorem. But that's exactly what Noether's theorem does. It's an inference from symmetries of dynamics to constraints on state transitions. So let me give you the standard statement of Noether's theorem in the context of quantum theory. It says, suppose you have some symmetry. So I'll talk about the unitary representation of that symmetry. So usually we just write it, so here capital L is going to be a particular generator of my symmetry. So in my rotational example, L is, for instance, the angular momentum operator for the axis about which I'm rotating. Theta is the angle I'm rotating by. So if I say that a system is undergoing closed system dynamics, so it's described by some unitary V, I say that the unitary V has the symmetry if it commutes with the action of the group, but that's equivalent to saying it commutes with the generator. So if my unitary commutes with the angular momentum operator, then I say, okay, it has that rotational symmetry. So that's the sense in which we say our closed system dynamics has the symmetry. And notice that if rho can go to sigma by some symmetric unitary V, then sigma can also go to rho by a symmetric unitary. It's just the inverse of V, which is also symmetric in that case. And Noether's theorem states that if that's the case, then the expectation values of all powers of the generator of the group are the same for the initial and the final state. So it's just a conservation law. So not only is the expectation value of the angular momentum conserved in the rotational example, every power of the angular momentum operator is conserved as well. So like the eigenspaces of the angular momentum operator are conserved, for instance. So that's what Noether's theorem says. It's just conservation laws from symmetries. And you all know the standard examples of which conservation laws follow from which symmetries. There are two deficiencies, I would say, with Noether's theorem. which I want to address with this resource theory. The first deficiency is that it says absolutely nothing about open system dynamics. From the very start, it imagines that it's closed system dynamics that's described by unitary, and it just makes no statement about the circumstance where your system might be interacting with an environment and evolving not by a unitary, but by a completely positive map instead. But as we saw in the last couple of slides, it's very easy to define what it means for an open system dynamics to be symmetric, just covariance with respect to the action of the group. So there's an obvious question, which is, what are the consequences of symmetries for open system dynamics? The second deficiency is that even if you're in the context of closed system dynamics, these constraints here, the conservation of other quantities, don't capture all the consequences of the symmetry. It misses some. And I could tell you more about that, but I haven't really got time today, so I'm not really going to explain why that's the case. But it's another good reason to try to do better. So the way we're going to try to fix this problem is by introducing measures of the resource that is asymmetry. So remember the definitions. So here, a function A for asymmetry is going to be called the measure of asymmetry. It's a function from states to reals. If whenever I can go from rho to sigma by a symmetric operation, possibly in open system dynamics, then the measure of asymmetry of sigma can't be greater than the measure of asymmetry of rho. So if I consider open system dynamics, which are irreversible, then every measure of asymmetry gives me a monotonicity constraint. So it should feel a little bit like the second law of thermodynamics. It says this quantity here is non-increasing. It would be like the negative entropy in thermodynamics. The negative entropy is always non-increasing in thermodynamics. That's the kind of constraint you'll get. But if you're talking about a closed system dynamics, so it's reversible, then the arrow goes both ways, the inequality goes both ways, and now I get an equality, so it gives me a conservation law. So every measure of asymmetry will still define a conservation law for closed system dynamics. Okay, so then the obvious question is, are the Noether conserved quantities that we just saw, these trace rho LKs, are they non-trivial measures of asymmetry? What do people think?
Yes.
Yes? I was hoping somebody would say yes, because the answer is no.
That's what I said.
Why not? Why are they not? So imagine a simple example where I have, just to say, a generator L, maybe we're talking about rotations about an axis, and two states, rho and sigma. So rho is just going to be a mixture of the eigenstates of L, whereas sigma is going to be a coherent superposition of those eigenstates. And the amplitudes here, when I square them, give me the weights in this mixture. So these things differ in their asymmetry properties. Rho is completely symmetric. If I act this unitary on rho, u phi dagger on other sides, the phase factors cancel out. It's invariant under the action. Whereas this guy transforms non-trivially under this phase shift. And so sigma is asymmetric, rho is symmetric. And so any non-trivial measure of asymmetry should be able to tell the difference between these two states. This is just what sigma looks like if I write it as a density operator. It has off-diagonal elements. But this difference is not seen by the Noether quantities because these Noether quantities, they're powers of L, and so they depend only on the diagonal elements in the L basis. They don't depend on anything else because they're just powers of L. So they assign exactly the same values to rho and sigma. They don't see the difference. So in fact, you can prove that any function of these Noether quantities is a trivial measure of asymmetry. It just assigns the same values to everything. And so they're not what we're looking for. They're not measures of asymmetry. Okay, so then the question becomes, how do you define measures of asymmetry? We have a definition, but how do you actually construct them? So this is the first place in the story where information theory comes in. So information theory is going to rescue us. And it's a very simple idea. I'm going to make a connection, a bridge, between this resource theory of asymmetry that I just defined and this resource theory of information I mentioned earlier on. And so the bridge is just this, that the following two conditions are equivalent. So if rho can go to sigma by symmetric operations, then the group orbit of rho, so that's the set of states I obtain from rho if I act every element of the group, can be taken to the group orbit of sigma under some transformation. Here, the transformation doesn't have to be symmetric. So the question over on this side is just, is there any transformation that takes this set of states to this set of states? But that, of course, is an information theory question, right? The resource theory of information we saw earlier was just, if I have an encoding of some classical variable, can this encoding go to that encoding? These are just encodings of a classical variable that ranges over the group. So the group orbit of rho is one encoding of a variable that ranges over the group. The group orbit of sigma is just another encoding of a classical variable that ranges over the group. And so on this side, I'm just asking, is the rho-based encoding, can it be taken to the sigma-based encoding under any data processing at all, under any map on the system? Okay, so let me just, first of all, prove this bridge lemma because it's critical. First of all, here's what it looks like in terms of diagrams. So I imagine that there's some symmetric, this is my code for symmetric state. So this is the definition of symmetric process, defined this way, taking rho to sigma. That's equivalent to, is there any process at all which takes the orbit of rho, so for every element of the group, the rotated version of rho to the correspondingly rotated version of sigma. And then the proof is only a few lines, but I find it better to get an intuition for why it's true. So I'm going to give you a physicist's proof. And basically, I'm going to show you that these two problems are just the descriptions that two different observers would give to the same problem. So imagine you have Alice and Bob. They do not share a Cartesian reference frame. And by that I mean, they each locally have some Cartesian frame in their lab, but they have no knowledge of what the relative orientation of their two Cartesian frames are. Okay, so they're ignorant of that relative orientation. And we're imagining that a system gets prepared in state rho relative to Alice's frame. So rho is the description of the state relative to Alice's frame. And it needs to be returned to her in state sigma relative to her frame. And Bob has to do some operation on it to convert it. So from Alice's perspective, she says, all right, I've prepared state rho. And then she asks herself, how would I describe Bob's operation relative to my frame? She knows Bob is going to do something specific relative to his frame. But relative to her frame, it's a rotated version of that. But she doesn't know what the rotation is. So she averages over all rotations. And when you average over all rotations, the process you get out becomes one of these symmetric ones, right? So any process I do, averaged over all rotations, becomes a symmetric process. So Alice says, the question is, can state rho be converted to state sigma by some symmetric transformation or not? But if I describe the same problem from Bob's perspective, he says, well, Alice has prepared some state rho relative to her frame, but relative to my frame, it's a rotated version of rho, and I don't know what the rotation is. So really, she's prepared one of a set of possible states in the group of rho, the group orbit of rho. I just don't know which she's prepared. And I need to return to her the corresponding element to the group orbit of sigma. That's my task. But now there's no restriction because the operation that Bob does is relative to his frame, so he can do anything he wants. So at the end of the day, he just says, can I transform this group orbit of rho to the corresponding element to the group orbit of sigma? It's exactly the same task, just described in these two ways. So anyways, that's one way you can prove this equivalence. What it means is that I can think of all these transformation problems in terms of information theory. So I think this picture is a kind of classical analog, helps. We start out with a problem which, a classical version of that problem might be, if I have this distribution on the sphere, can I turn it into this distribution using rotationally symmetric operations, right? And here the answer seems like it's yes, I could just add some noise and it'll spread it out a bit. But the point is that this question is equivalent to this question, which is, if I've encoded a direction on the sphere in a rotated version of this original distribution, so for example, for these two particular orientations, I could encode it in this or in this, can I transform that into this encoding of that direction? Is there any process I can do that will transform this encoding of the direction on the sphere into this encoding? It's ultimately the same question, that asymmetry properties of a state ultimately are just questions about how much information that state has about the group element, how much information it can encode about the group element. My clock says I've been going for 35 minutes. So is that wrong, or?
Mine says 2:10 and we started at 2:30.
We started 2 minutes after.
It's okay. I'm going to go overtime anyhow, so it doesn't matter. Anyhow, so.
As long as everything- no problem.
So one of the consequences of this is that if I ask, to find measures of asymmetry of a state, ultimately I can get any such measure by just trying to quantify the information about the group that's encoded in the group orbit of rho. So if you just give me any standard measure of information and apply it to the group orbit of the state, you get a measure of asymmetry. So I gave you this sort of 3 examples of measures of information that quantum information theorists like, and I just put them through the crank and I can derive measures of asymmetry. So this one asks me to take the state, average overall rotations of the state. Typically, if it started out asymmetric, when I average overall rotations, I get something that's more mixed, has higher entropy than the original state, and so this difference becomes positive. It's a measure of asymmetry. The amount of non-commutativity between rho and the generator of the group, we saw that that was critical for being asymmetric, measured by this norm is also provably a measure of asymmetry. So you can generate, again, a long list of these things, and if I were talking more about asymmetry, I could give you lots of nice examples of how you can apply these measures of asymmetry to various interesting problems. But let me just focus on rehabilitating Noether's theorem, overcoming those deficiencies. So now when you say, suppose rho can go to sigma by symmetric operations, you can immediately infer a bunch of necessary conditions. So for any one of these measures of asymmetry we've derived, if this is true, then that measure should be non-increasing. Now these are monotonicity constraints. They're true even for open system dynamics. Good. If you ask to solve the problem completely, have necessary and sufficient conditions, you really need to solve this problem, find a complete list. And again, that's an open problem. So even though we have this nice connection with information theory, it's an open problem in quantum information theory. It's an open problem here. But we can leverage certain known solutions, like for the case of pure states. We can leverage some results from information theory and get a necessary and sufficient conditions for convertibility. So we now know, for pure states at least, exactly what that partial order looks like. And so we don't have to rely on some set of measures. We can just apply this criterion here. Good. So all of that is a bit of a setup for the topic that's more pertinent to this conference, which is the resource theory of athermality, so deviations from thermal equilibrium. So there, the motivation is really the second law of thermodynamics. So here's, I think we've already seen something like this. This is the usual kind of statement in terms of heat and work. No thermodynamic process whose sole effect is to transform heat extracted from a source at uniform temperature completely into work. But there's also these entropic forms of the second law, which I think you could say originated in Clausius's work originally, or were motivated by it. And there you find a lot of disagreement among the textbooks. So what I'm giving here is a kind of standard thing that I've sort of distilled out of many textbooks, but I think it captures a kind of standard notion. All physical systems in thermal equilibrium can be characterized by a quantity called entropy, which cannot decrease in any process in which the system remains adiabatically isolated, which means shielded from heat exchange with the environment. So that's meant to be sort of the gold standard of the second law. And just as there was deficiencies with Noether's theorem, I see a lot of deficiencies here. It says nothing about systems that are out of thermal equilibrium. So we'd like to know, for example, for two states that are non-equilibrium states, can I make a transition from one to the other? It says nothing about systems that are not adiabatically isolated. Just like in the case of Noether, where we had open system dynamics, I can imagine a system that's coupling to its environment, and I might want to know whether a given state transition is possible in that circumstance. It doesn't apply to systems that are microscopic. It hasn't been stated here explicitly, but typically these formulations rely on taking the thermodynamic limit. They're not meant to apply to individual systems, so we'd like to know whether certain state transitions are possible for individual systems. It says nothing about the quantum case. should I just turn Shannon entropy into von Neumann entropy? Is that all that happens when I go quantum, or is there something more? And then finally, as I'll show you, it turns out that this non-decrease of entropy is not a sufficient condition for inferring that a given thermodynamic process is possible. So in cases where it's actually a valid constraint, it's only a necessary condition, not a sufficient one. So the resource theory of athermality can overcome all of these deficiencies of the standard statement of the second law. And if there's time, at the end, I'll say a bit about what the resource theory of athermality tells you should say in the context of Maxwell's demon, and whether we should think of Maxwell's demon as a violation of the second law or not. The answer is going to be no. Okay, so as we do in any resource theory, we start by specifying what the free operations are. So the philosophy here is that we want to allow for free stuff that won't allow us to do arbitrary amounts of work, right? So if I allowed too much stuff for free, then I could just do as much work as I like, and that would not really be capturing thermodynamics. So we want to define a subset of operations from which I can't do work for free. Work becomes a resource. So the first constraint that you need is that any unitary you're allowed to do has to be energy conserving. Because if you didn't have that constraint, I could take a two-level system and I could apply a unitary that would take it from its ground state to its excited state. And that's an example of doing work. And so I don't want to allow that. So the unitaries I allow have to commute with the Hamiltonian of the system. They have to conserve the energy. The second constraint is that I can only prepare systems in a thermal state at some fixed temperature. So this is just, so gamma will be my notation for the thermal state of a system with Hamiltonian H at temperature T. Z is the partition function here. So the idea is that this is very much like having a bath at some temperature T. So here we say, well, look, you can take any system you like, prepare it in its thermal state at temperature T, and you can prepare as many as you like, which means you can have an arbitrarily large bath of any kind of system you like, but it's all just at temperature T in its thermal state. That's all free. Now, note that much like in the resource theory of asymmetry, you had to choose a group to get going. Here, we have to choose a temperature. And so that means that this resource theory is really a pragmatic thing that depends on your circumstances. So if I want to know what are useful resources for work here at room temperature, I'll use the resource theory where T is set to room temperature. And then anything that deviates from room temperature is a resource to me, and I can quantify it. But if I'm off in intergalactic space and the ambient temperature is 3 degrees Kelvin, then the resource theory I should use is for a temperature 3 degrees Kelvin, such that anything that deviates from thermal at temperature 3 degrees is now a resource to me, and I can do work with it. So it is dependent on your context. Now note that if I give you now a different thermal state of the thermal form, but at some other temperature, that's a resource here. So a thermal state at temperature T prime is a resource in the theory with background temperature T. It's like having two heat baths that you could extract some work from. Okay, and then the final constraint is that I can always just ignore some systems. So I can always trace over any subsystem I like. And that's it. That's everything I can do for free in this resource theory. And what that means is that if I'm considering an individual system, and I'm asking what completely positive maps can I implement for free, I can again use this dilation. I can say, well, I can take my system, I can couple it to any ancilla I like, as long as it's prepared in the thermal state. I can couple the two together by a unitary that commutes with the Hamiltonian, and then I can trace over some part of the final system, and I'll call that a thermal operation. So any map that can be written in this form is allowed for free. You can do it as much as you like. That's how we define the resource theory. Good. So we ask the standard question. Can I find conditions such that a state rho can go to a state sigma by some thermal operation? What are the constraints on state transitions that arise from the constraint that this evolution is thermal? And I'll say a little bit about the full conditions later, but let's start simple and just talk about necessary conditions. So can we find measures of athermality, measures of how far you deviate from being a thermal state? So again, that's just a function which is non-increasing under these thermal operations. The same story as we had before. And once again, this is where information theory can help you out. you can make a bridge between the question you're interested in and a question about information theory. So if rho can go to sigma by thermal operations, then this set of states, so this set of states here is the group orbit of rho for the group of time translations. So just consider rho and all of its time translated images for every possible interval, together with the thermal state for the system that rho is defined in. So that gives you a set of states, and the question is, can that set of states be converted to the set of states which is the group orbit of sigma under time translations, together with the thermal state for the system that sigma is defined on. So you can show that the arrow definitely goes this way. There's no proof that the arrow goes this way as well, but I conjecture that it's true. I believe that this provides the necessary and sufficient conditions for this being true, but I don't yet have a proof. All right, so maybe I will skip the proof. Yeah, let me skip through this. You just have to take my word for it. But yeah, let me move on to a slightly simpler example, which is the example of states that are time translation invariant. So we're not talking about all states anymore. We're just talking about those which under time translations are fixed. In that case, I can have a bridge lemma where I can prove that I have necessary and sufficient conditions. And it's this, that if rho can go to sigma by a thermal operation, then there exists some operation, not necessarily thermal, that takes the thermal state for the system on which rho is defined to the thermal state on the output. And it takes rho to sigma as well. So in other words, it transforms this pair of states to this pair of states. So this is a problem in information theory. It says if I've encoded a bit of information in rho and gamma, that pair of quantum states, can I convert it by any data processing into an encoding of that bit in terms of sigma and gamma? That's just a question that quantum information theorists are familiar with. It's about encodings of a single bit. So if you give me any measure of the statistical distinguishability of a quantum state and the corresponding thermal state, that is a measure of how much this state deviates from being a thermal state for these time translation invariant states. So we can immediately get a bunch of measures of athermality. In particular, what you can find is that if you look at three particular states, these are the energy levels, and you ask, what are their athermality properties, you just need to compare them with the thermal state, right? So it turns out that my first choice was the thermal state for that temperature. Here's the thermal state for that temperature again to compare. So this is a ground state. It's obviously statistically distinguishable from the thermal state. This excited state is even more statistically distinguishable from the thermal state. This guy is not at all distinguishable. So rho S2 is more athermal than rho S1, and rho S3 is even more athermal than that. That's the idea. It's this distinguishability that matters. Yes?
And distinguishability, is that trace norm distinguishability?
Well, again, you have lots of options.
Okay.
So again, for take your favorite measure of statistical distinguishability from quantum information theory, of which there are many, and you can convert it into a measure of athermality. So one nice one is if you take the relative entropy measure of distinguishability, you convert that through this bridge principle into a measure of athermality, you get what I call the free energy excess. So it's the free energy of your state rho above the free energy of the corresponding thermal state for that system, where this is the definition of the free energy. And that case, you can show reduces to negative entropy in a certain limit. So if I consider this as a constraint on state transitions, so if rho goes to sigma, then this free energy excess cannot be increasing. And then I write that out in terms of these definitions. It's this inequality. If I then tell you that your system is adiabatically isolated, which means that the energy term doesn't increase, then I just get this expression here. And if I tell you that the output system S prime is exactly the same as the input system S, so that the thermal states are the same, then these two terms cancel, and I just get back to the standard form of the second law. So we can rederive for this measure the usual form when the systems are adiabatically isolated, but of course it applies more generally. And if you want, you can use this trace distance measure, you can use relative Rényi entropies, and you can get a long list of measures of athermality, and different measures are useful in different contexts. So the point is that at least for these time translation invariant states, you get a rehabilitation of the second law where you don't just have this entropy increase condition, you have a long list of conditions for every measure of athermality, monotonicity constraint. And you'll note that it holds for quantum systems. I didn't have to say that rho or sigma were in thermal equilibrium. There were any states. I didn't restrict to the case of adiabatically isolated systems. These guys could be exchanging heat with their environment. And finally, these could be states of a single spin-a-half system. There's no thermodynamic limit going on here at all. Good. If you go back to the general case, where states are not time translation invariant, then you had this more complicated condition, as I say. And the real reason behind it, I didn't go through the proof, but the real reason is that these thermal operations, because they're defined in terms of energy conserving unitaries, they are time translation invariant. So if I first do a time translation and then I do one of these thermal operations, that's the same as doing the thermal operation and then the time translation. So they are an example of a symmetric operation. All thermal operations have a symmetry, time translation symmetry. And so it means that all the athermality properties of your system have to include the time translation asymmetry properties, right? You can't change your time translation asymmetry properties under thermal operations because your thermal operations are time translation symmetric. So all your time translation asymmetry properties cannot increase. They also have to be monotonic. So in particular, any measure of time translation asymmetry of rho, so I already showed you a whole bunch of measures of asymmetry for any group. You can work that out for time translation asymmetry. They are also measures of the athermality of the state rho. That you give me a state and it's not time translation symmetric, then it's clearly not a thermal state. It must deviate from thermal, so I can measure its deviation from being thermal in terms of these guys. And so I can now add to this list of measures a bunch of these measures of time translation asymmetry, and they are also necessary conditions on this thing being possible. So this is an extra rehabilitation of the second law, these kinds of constraints. But what's interesting is that I think you should think of these more as a rehabilitation of the first law, because when you look at the first law of thermodynamics from the perspective of Noether's theorem, it's really just an application of Noether's theorem. It says if I have time translation symmetry, then energy should be conserved. I would say that modern textbooks in thermodynamics shouldn't state the first law of thermodynamics as some fact about thermodynamics. It's really just Noether's theorem. And if you give me some other sorts of symmetries, I get other conservation laws. That's really what the first law of thermodynamics is. These monotonicity constraints on asymmetry should be best thought of as being in that category. So even if I have open system dynamics, I might not have energy conservation anymore, but every time translation asymmetry monotone is not increasing. It's an addendum to the first law of thermodynamics. Good. All right. So if you try to find a finite set of conditions that are necessary and sufficient, you'll find it's an open problem. Right now, we only have a solution for the case of the time translation invariant guys. Although the solution wasn't obtained by appealing to this bridge lemma, to information theory, it was first obtained by these guys in 2013. It's very easy to rederive their solution using this insight and known results in the literature. But I think I don't have time to go over the solution, even though I really like it and I need it to talk about Maxwell's demon. So why don't I stop, and if anyone has questions about it, let me just go to my concluding slides. But I'm going to skip over the Maxwell's demon stuff and how that works. You can ask me about it if you want. Let me just wrap up. What I've tried to persuade you of is that the asymmetry properties of a state are really just about its capacity to encode information about the symmetry group. The athermality properties of a state have to do with the state's statistical distinguishability from the thermal state, together with its time translation asymmetry properties, which are really properties about how it encodes information about time translations. Possibly some others, although I conjecture there's nothing more to be added to this list. Which means that both of these properties are information-theoretic notions, ultimately. That the asymmetry and the athermality are really about informational properties. And I gave you rehabilitated versions of Noether's theorem and the second law of thermodynamics, and ultimately they boil down to specific instances of the information-theoretic principle that I told you about early on, which is that you can't increase information under data processing, right? So once you show that these symmetric and thermal operations are really just examples of data processing, they're equivalent to a problem involving just data processing, then to deny either of these forms, these principles that we derived, would be like saying, Alice sends Bob some encoding of a classical message, and Bob can magically somehow get more information about it than if he had had the original encoding. That's, to my mind, just logically inconsistent. Like, it seems to me that the principle that you cannot increase the measure of information under data processing is very solid, and therefore these principles are equally solid. Okay, what's the take-home message? Any second law, like the ones, the original one or these rehabilitated ones, should not be thought of as stating that conversions are either impossible or improbable. They're really just about talking about how expensive a given conversion is under the restriction that you only have access to thermal operations. You can think of all this as, I mean, really it's saying, what could you do in principle? And it says nothing about how you might achieve this. It just says, if you could do any thermal operation, here's what you could do. But there's a question of, well, can I build a machine to achieve this particular thermal operation, to do this conversion? That might be hard. So the question of whether we have access to machines that can accomplish these things, that's a different question. So this whole resource theory approach says nothing about what sorts of machines, for example, will arise naturally in the world. So, living organisms manage to do work. They use a reservoir, say through photosynthesis, and they do work. They're sort of a naturally occurring machine that can do these conversions. Nothing in the resource theory says anything about what sorts of machines like that will arise. That kind of question, which I think has been the focus for a lot of discussions of the foundations of thermodynamics, is not really addressed by the resource theory. You would really need this dynamicist conception of physics to address that sort of question. And let me stop there. Thanks.
Questions?
Thank you very much. I think this was quite astonishing, especially the asymmetry and the can you go back to where you have where you have your particular inside, where the athermal
Sorry, wait, say it again?
This one, exactly.
Here, yeah.
So one of your criticisms was that the second law, the non-decrease of entropy is not sufficient condition for inferring that it would be thermal operation can take place. But here on the right-hand side, it's also just necessary conditions, or not sufficient.
That's right. Here we're adding necessary conditions in addition to the usual one, but we're not proving that this is a sufficient set. This slide is really about asking, can we find a necessary and sufficient set? And currently that's an open problem. And it's open only for the case where you have time translation non-invariant states. So if you focus your attention to just these time translation invariant states, then we do have necessary and sufficient conditions. So I didn't have time for that, but thank you for asking, because now I can answer this question. Here's what the necessary and sufficient conditions look like. So again, if rho and sigma are time translation invariant, then ultimately they boil down to just specifying probabilities of being in different energy levels. So I can characterize rho and sigma by just distributions over the energy levels. And the important thing is, how distinguishable are they from the thermal distribution for that same type of system? So I want to know whether, for example, this rho can go to this sigma in a resource theory at temperature T, for which these are the thermal states. So the prescription is this. Take the pair of values for every one of these energy levels, take the probability, so these circles are just meant to represent the probability you assign to that level. So big circles mean higher probability. So P3 is a higher probability than P2 or P1. So the thermal state is dropping off in a Boltzmann distribution from high probability to low probability. So you just take these pairs of values, P3G theory, and on the y-axis here you plot the P values for a given level, and on the x-axis you plot the G, so this is the P3G3 point, So it has a large value of P3 and a small value of G3. And then over here, you've got something which has a smaller value of P2 and a bigger value of G2. And here, you've got something which has a small value of P1 and a large value of G1. And then you take what's called the zonotope of those vectors. I'd never heard of that before, but it's a linear combination of these guys where the coefficients are between 0 and 1. So I can add up these vectors any way I like, but only using coefficients between 0 and 1. So in particular, I could add them all up with coefficients 1, and then they go to this point, because all these x-coordinates add up to 1, and these guys add up to 1, so I get up to here. But if I just take this guy with coefficient 1, these guys with coefficient 0, I get to this point. And if I add up this guy and this guy, I get up to this point. So I can fill in everything in this polytope region in that way. And I can do the same thing down here. And then the condition is, does this polytope include this polytope or not? So in this particular example, it does. And so I can go from rho to sigma. So these curves are actually familiar. They go all the way back to some work in economics where they're called Lorentz curves. And they tell you something about the deviation from the straight line. So here, if my state were free, if it were thermal, all these vectors would be just aligned on the diagonal, and I would just have a straight line. And all these things tell you how far you are from that straight line. So this shape is further from the straight line than this one is. And in that sense, it's more athermal. So these are the necessary and sufficient conditions. And so now you give me any state you like, and I can just plot its curve, its zonotope, and I can put it into the partial order, and I can specify whether it's above other shapes or not, just based on this geometric inclusion relation. And so, for example, these two guys are not ordered relative to one another because this does not get included in here, or vice versa. And so I know, for example, that different measures of athermality will order these two guys differently. And that's something you never could have gotten if you just focused on the negative entropy alone, right? It would have induced a total order on these guys, and you would not have seen the lack of convertibility of these states.
Questions? Yes?
How does these be time transition invariant? Seems like a very restrictive condition. Can you comment on that?
Yeah, I think I agree. I mean, in one sense, a lot of conceptual issues in thermodynamics can already be addressed just talking about those kinds of states. So in that sense, it's, we can talk about, for example, the Maxwell's Demon problem without necessarily having to talk about time translation non-invariant states. But it is, I would agree with you in the sense that once you're down to the time translation invariant case, because all energy conserving operations are free, even if your energy eigenspaces are not one-dimensional, right? So even if a given energy eigenspace has there's sort of room for coherence within that energy eigenspace, I consider it, every transformation within that space is free. So I can always convert everything to some default basis, right? And then do all my problems in that one preferred basis. So ultimately, it reduces to a classical resource theory where the quantum states are all just diagonal on some fixed basis. And that's why it's easy to leverage this bridge to information theory to solve it, because the classical case, we knew the solution. And so the case of time translation non-invariant is where you really have some quantumness, some genuine quantumness. Things are not all diagonal on the same basis. And so it's the more interesting case. But ultimately, if my conjecture is true, it really boils down to characterizing the time translation asymmetry properties of these states. That's what we're kind of missing. So we don't have the necessary and sufficient conditions in the resource theory of asymmetry, and therefore we don't have them in the resource theory of athermality either. So if we could finish the project of the resource theory of asymmetry, which ultimately rests on finishing the project of the resource theory of quantum information, then we could have necessary and sufficient conditions over here in athermality.
Further questions? Going one? Oh, wait.
Since we have time, I want to hear what you were going to say about capital D.
All right. Good. So the question is, should we think of the fact that Maxwell's demon can sort atoms into hot and cold as a violation of second law? This resource theory approach you can think of as a kind of vindication of the Landauer-Bennett response to this problem, which is that if you decide to treat the daemon itself. Like the spirit of this resource theory approach is the only things you should grant yourself as free are the things that have been specified, the thermal operations. And so if somebody says, I want to imagine that I have a daemon who does this and that, then the first question is, well, should we think of that as a costly addition or a free addition? So we have to ask, well, is the daemon really just coupling in an energy conserving way with some thermal state? Answer, if the daemon has a memory bank and the states of that memory are not thermalized but rather initialized, then no, it is not a thermal state. So the daemon itself is a resource of athermality. And in particular, if I look at, for example, a bit in the brain or in the memory device of the daemon as a two-level system which are energy degenerate, for which the thermal state is, of course, just a uniform distribution. So that just follows if I take e to the negative Hamiltonian over kt, where the Hamiltonian is trivial, 0, then it just says, oh, it's the same probability for all the levels. So this is the thermal state for that bit. Then to imagine that it's initialized with all the probability in one of those two states is to imagine a deviation. This is statistically distinguishable from the thermal state. So this is an athermal state. And you can draw its zonotope in this representation. And it looks like this. And you can, for example, find that for some other system, this is like a three-level system where the energies are different, there's a particular state which has exactly that same zonotope. That means these guys are equivalent resources. So the point here is that even though this doesn't feel necessarily like a thermodynamic resource, it's energy degenerate and it's sort of a resource of information. It says I'm not completely ignorant of which it is. I know which side it's on. That might feel very different, but in the language, from the perspective of this resource theory, it is an absolutely equivalent resource to having something that is in its ground state relative to the thermal state. And therefore, it's you can extract work from this just as much as you can extract work from that. And ultimately the answer is, yeah, we use the initialized memory of the daemon as a resource of athermality, and there's a certain amount of work we can extract from it. And so the fact that I can increase the temperature differential is not a surprise. It'll just be limited by the original memory capacity of the daemon.
Question?
So here at the beginning, you mentioned measures and partial orderings. And
yep.
Just talk figuratively about the relation between the two. So is it the case that a number of measures will help you discover the partial ordering? How does that work?
Yeah. So the idea would be something like this, that what I would like to have ideally is some conditions I can evaluate. You give me a pair of states, rho and sigma. I'd like to be able to have an algorithm that'll tell me whether rho can go to sigma or not. So if I have an algorithm like this one, which just says, all right, take where did it go? Take your two states, compute their zonotope, see if one's included. That's an example of such an algorithm. And it's not described in terms of monotones, right? So I haven't said anything about the measure of athermality here. But another algorithm would be, maybe I theoretically can deduce that this list of n monotones, athermality monotones, is a complete set in the sense that if the value of each of these monotones is greater for rho than it is for sigma, greater or equal than, then yes, rho can go to sigma. So you can look for ways of expressing the necessary and sufficient conditions in terms of a list of monotones. And the point is just that if you find that the order relation is not a total order, but rather a partial order, then you know immediately that list of monotones that will be sufficient for deciding convertibility will have to have more than one element in it, right? So there's no possibility that the negative entropy on its own could have decided this. It's going to have to be a list. It might even have to be an infinitely long list of monotones in some cases. Does that answer the question?
Wait.
Can you back your pen off the slide where you're talking about this before?
Sorry, these slides? Yeah.
Okay. Maybe I just wasn't paying attention. So, what's the sort of criterion for counting something as an information
theoretic notion. So just having capacity to encode information makes something an information theoretic notion or something more.
Well, I guess I mean it in the following sense, that the kinds of things that have asymmetry properties are not the physical states of an object, but rather, I would say, epistemic states of an object, or quantum states of an object, things that are meant to encode information. So let me give you an example, which didn't make it into the talk. If I take the following example, which is meant to be a potential challenge to Curie's principle. Okay, I have a column, and I put pressure on it, and eventually it buckles. So originally the column was cylindrically symmetric, but then I put the pressure on it, it buckled, and it chose the direction it buckled in. So you might say, oh, is that a violation of Curie's principle? Because it looks like initially I have something that's symmetric, and finally I have something that's asymmetric. So I think the perspective that this gives you is that that's not a violation of Curie's principle, and nor is it even a violation of the quantitative Curie's principle. Here's why. The reason the column buckles, or the direction it buckles in, is determined by defects in the column. So there's maybe some atomic defect which decides that it's going to buckle this way as opposed to anything else. And then you might have said, okay, well that solves the Curie's principle, but what about the quantitative Curie's principle? Wouldn't you say that an entirely buckled column is much more asymmetric than a column that's merely defective by one atom? To which the response comes, a single atom is just as good at picking out a direction in space as the topmost atom of the buckled column. That ultimately the original column and the buckled column, in terms of their capability of encoding a direction in space, only have a one atom's width resolution. And so there's nothing about the information carrying capacity of the original column or the buckled column that's different. That's what's important to its asymmetry property. It's its information carrying capacity. Nothing about the physical configurations. So in particular, if I had a state of knowledge of my column, I knew that the defect was sort of in this range, and I asked, well, what would I know after it was buckled? Well, I would know it's buckled somewhere in this range. It's my knowledge that gets preserved under these symmetric operations. Is that?
Yeah, I mean, that's good. My worry, and actually you might not be worried about this, is that if, given distinction between two kinds of physical states has information carrying capacity that could be used to carry information, then it sounds like not only are these information theoretic notions, could there be any notion in physics that isn't an information theoretic notion?
That's good, yeah.
Could there be any notion of physics that isn't an information theoretic notion?
Or would you be happy to say that the invasion is in fact a complete takeover?
I don't have the impression that all properties ultimately boil down. Like, if we think of different things that I might measure in physics, I don't think I could run the same argument that ultimately they're measuring capacity to encode information. Like, take the temperature. That was a parameter that appeared in my talk.
Okay.
Nowhere, I think, did I give any argument that, two different temperatures, should be thought of as, or a variation in temperature should be thought of as encoding information about something else, or it's.
You didn't, but it seems like you could. Like, if I wanted to, I could send you a message by sending you, taking an iron ball and heating it to a certain temperature, depending, choosing between two temperatures depending on which message you want to send.
Right.
You can send that, you measure the temperature.
Right.
So temperature has capacity.
Sure, but there is that. I agree that, just information is physical. So every time I encode information, I have to do it in some physical degree of freedom.
Right.
And furthermore, every physical degree of freedom is a candidate for encoding information. So
Right.
yeah, I agree with that. But that's not the sense in which I mean it here. Here what I'm saying is that the particular measure of asymmetry, so there's a program here for talking about quantifying asymmetry. boils down to, this bridge principle shows that that's ultimately a measure of information carrying capacity. And what's a measure of information carrying capacity? Well, things like the Halevo quantity, the one norm distance between, so it's like those are measures. Not any old thing is a measure of information carrying capacity. So I think that's a much more non-trivial sense in which you can be information theoretic. Like if I say every measure of this quantity boils down to one of this very strange list of things. Like you won't find Halevo's quantity in the physics textbooks. You won't find these relative Rényi entropies. Those are not things that were natural to physicists to write down. And so to discover that every measure of asymmetry is actually one of these things in disguise seems to me to really be a kind of advancement in the front
Okay,
from
so
information theory into physics.
every measure of this quantity
Yes.
is a measure of information carrying capacity.
Right.
Okay, so that I can see that takes some work to be shown.
Thank you very much.